Good afternoon to everyone. I welcome all of you to the 63rd lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University with the support from RUSA 2.0. Today we have a speaker from University of Hong Kong, and it is my pleasure to introduce you today's speaker, Professor K.W. Chow. Professor Chow completed his undergraduate studies at the California Institute of Technology, or Caltech, USA, and obtained his PhD from Massachusetts Institute of Technology, United States of America. He stayed at Massachusetts Institute of Technology briefly as a postdoctoral fellow and moved to University of Arizona. He joined at the University of Hong Kong in 1996. He is a well-known person in integrable systems community. Professor Chow's research interests focus on fluid mechanics, nonlinear waves and solitons, and optical fibers and communications. He has also worked extensively in biomedical engineering fields, for example, the applications of continuum mechanics to blood diseases. He is serving as a deputy editor of the journal Wave Motion and serves in the advisory panel of the journal Physica Scripta by Institute of Physics, UK. With this short introduction, now I invite Professor Chow to deliver his lecture. Over to you, Professor.
Okay, so thank you. Thank you for the kind introduction. So let me start the talk by introducing this subject. So I will try to speak slowly because we are on an online mode, so things like computer transmission may take time. So I'll try to speak slowly. And if you cannot hear me at any time, just or do not understand anything, feel free to interrupt by using this raise hand option and so on, or just interrupt by saying something through the microphone. Okay. So today we thank the organizer for giving me this opportunity to talk about this particular topic: Hirota Bilinear method, soliton, rogue wave, and the Fermi-Pasta-Ulam-Tsingou recurrence. Okay, so the first part of the talk will be mostly for kind of beginning researcher, graduate student, and so on. So for those experts in the audience, please bear with me for the first 20 minutes or so, where I try to introduce this particular area of study. For the second half of the talk, I will talk about more advanced topic, current research topic, like rogue wave, briefer, and this Fermi-Pasta-Ulam-Tsingou recurrence. Okay. So to begin with, let me say something about solitons. Okay, so what are solitons? Solitons are localized mode. Localized means the mode, the displacement is confined to a certain neighborhood in space, and they are decaying in the far field. So solitons are localized mode propagating over a long distance by balancing two effects. One is dispersion, the other is nonlinearity. So solitons are first discovered in the 1960s, and then they has been extensively studied in the past 60 years. To begin with, let me start with kind of the first, or one of the first few soliton equation known as the Koldewey-de Vries equation, or sometimes we'll just call it KDV equation. So what that is an equation arising from shallow water wave where we have a dependent variable, u as a function of x and t, space and time, such that the first time derivative 6 times ux, and then u3x derivative is equal to 0. So if we analyze this equation by looking at the key terms of the equation, the first part is ut plus 6 times ux equal to 0. Now, these two terms will describe nonlinear effects, and if you include these two terms alone, or nonlinear effects alone, then you will have breaking waves. On the other hand, if you have ut plus u free x derivative and these two terms alone, then you will have the effect of dispersion, and then you will have a disintegration of the waveform. Now let's try to do this thing in a very elementary manner. Now suppose you have ut plus c times ux equal to 0. Again, subscript being a derivative, where c is a constant. Then the general solution can be found, and that general solution is a function of x minus ct. So namely, physically, it represents a wave going to the right if c is bigger than 0. Now, if you have a more complicated case, ut plus ux equal to 0, now if you want to solve this equation exactly, actually you can, and that method is called characteristics of partial differential equation. But again, I try to avoid very complicated mathematics. I try to present everything in a simple, physically intuitive manner for the beginning researcher of this field. So if you look at the first equation, ut plus cux equal to 0, then you have c being the constant, will turn out to be the velocity of the wave. Now, if you do it in a very artificial manner, it's not exactly right, but to give you the qualitative feature, ut plus ux equal to 0, if I claim that this is a wave, then the wave speed will be proportional to u. Of course, that's not strictly speaking right, but let's see if what will happen. Again, let me try to do a very simple qualitative explanation. Again, excuse me for this artistic, my poor artistic sense, though that is the best diagram I can come up with. I kind of take this analogy from a book by a Japanese author when I was a graduate student. So suppose you line up a group of people, and let's say the tallest person you put it in the center, and then the shorter person you put it at the two ends of the group, and you ask this group of people to walk, let's say, to the right. And if it happened that all persons walk at the same speed, then this whole pattern will just move to the right because everyone is walking at the same speed. This is what happened when c is a constant. Now, suppose you argue that a taller person walks faster and the shorter person walks slightly slower, then what will happen is that the taller person will catch up with the shorter person, and therefore the front part of the wave will kind of accumulate and pile up, but whereas the back part of the wave will kind of spread out. Now, the mathematics, of course, is more complicated than that, but this is give you the qualitative feature. And in fact, this has happened in many wave situations where the wave, whether it consists of light or water, it's the same thing. You have a pile-up effect, you have a nonlinear effect, and then eventually wave breaking. Now, the other end of the spectrum, dispersion. Now, I guess a lot of you will have learned this dispersion from secondary school physics. So you have a very dark room, you have a glass prism, you open the door slightly, you let a very narrow beam of sunlight come in, and that narrow beam of sunlight going through the prism will spread the white light into the red light, yellow light, blue light, and so on. And the conventional explanation is that the red light, blue light, yellow light travel at different speed in glass, and therefore you have this kind of dispersion. Now, dispersion is in fact a general feature of wave propagation phenomenon, and is not restricted to light. Okay, so suppose we go back to the linear part of the quadratic derivative equation, ut plus u free x derivative equal to 0. Then if you look for a solution exponential ikx minus omega t, then when you substitute this into the differential equation, you'll find that omega equal to minus k cubed. Omega is the angular frequency, k is the wave number. Sorry, I actually omit the I in front of the omega. But eventually the phase speed, which is the angular frequency divided by the wave number, is minus k squared. So the component of the components of different wavelength will move with different speed. In other words, whenever the phase speed depends on the wave number, you will have a dispersion effect. Okay, a very simple example will be, let's say we are teaching a class, and at the break, we ask all the students to go for a break. They can go to the canteen and some food, And if this whole group of students walk at the same speed, they will arrive at the canteen at the same time. But of course, if each student walk at a different speed, this group of students will spread out. In other words, you have dispersion. Okay. So let's say we have a very schematic numerical simulation. If you do not have dispersion, you have this kind of the black pulse where the whole pulse move along. But if you have dispersion, each component will kind of separate, and then eventually the wave profile will spread out due to this dispersion effect. Okay. So now what happens if you have breaking effect and dispersion effect coming together? And if somehow they balance each other, then you can, in principle, have a propagating wave, which turn out to be what we call a soliton solution. Okay, so if you do a very simple-minded calculation, a traveling wave of the quadratic degrees equation, again, I omit all the calculation. So you go through some kind of conversion from a partial differential equation to an ordinary differential equation, integrate 2 times, and so on. Then you will find that the solution is a so-called hyperbolic secant square. Hyperbolic secant is called, of course, a reciprocal of hyperbolic cosine. And then the solution is dependent on one parameter, alpha, which is given as such, alpha square over 2, hyperbolic secant square, and so on. So the physical interpretation is that this is a wave of elevation traveling to the right because the speed is alpha square, always positive. Okay. So I'll explain, if I have time, I'll explain the fluid mechanics significance of this particular solution. But now let's focus on the mathematics first. Now, suppose I want to rewrite this particular solution, hyperbolic secant solution. And again, at this point, it sounds very artificial. Instead of u, I write this as 2 times log of an auxiliary function f and then 2x derivative. Okay, so you might find that very artificial or meaningless at this stage, but nevertheless, please bear with me. If I have this hyperbolic secant solution and I insist on writing it as 2 times log auxiliary function x derivative, you'll find that that auxiliary function is 1 plus a very simple exponential. Okay, so the idea, or this idea, can be exploited by the Japanese scientist Ryoko Hirota back in the 1970s. He just looked at all these expression and generalize it, and then this particular method is called the Hirota Bilinear method. So the main result is that the Hirota Bilinear method is capable of finding exact multi-soliton solution of nonlinear equation using differential calculus alone. Okay, so that is the last phrase is the most remarkable one. Using differential calculus alone, you do not need even to do integral calculus. You do not even need to do integral. Okay, so in principle, any secondary school student who has some knowledge of calculus can go ahead and perform calculation with the Hirota Bilinear method. Okay. Okay, so now let's see what kind of magic the Hirota Bilinear method can help us to solve a nonlinear partial differential equation using differential calculus alone. Okay, now let's go back to the same quadratic degrees equation, ut 6 times ux, and then u3x derivative equal to 0. So again, somehow I have u equal to 2 times log f xx. And again, you can see right away there will be a lot of differentiation involved. And the differentiation seems to be up to 5th order because you have 3x derivative. U itself is 2 log f, 2x derivative. Your intuition will tell you that I need 5x derivative. But again, the ingenuity of Hirota is that instead of doing 5 derivative, he integrated the equation once, and the equation will have 4x derivative, and using a very special bilinear derivative, he turned that into this particular formal equation. I introduced something called capital D, where this capital D is called the Hirota bilinear derivative. So let me show you what that derivative is. Okay. Okay, so that derivative, I hope you can still see the screen, right? So that particular derivative is given in the following form. Okay, so if you have, let's say, small g, small f as function of x and t, then I introduce a derivative as follows. Okay, so the first function, I have the independent variable as x and t. The second function, I introduce artificial auxiliary variable x prime t prime, and then I go through this particular derivative ddx minus ddx prime, and then raise it to m time, go through the differentiation, and after I'm done, I set x equal to x prime. So again, not even integral calculus involved. You don't need to do integration by part or whatever fancy integration. You just need to do differentiation. You just go through this differentiation according to this particular prescription. Then the ingenuity of Hirota is that the quadratic de-Riesz equation can be written in the following form: dx dt, where capital D is the Hirota operator, and then dx to the fourth f dot f equal to 0. Okay, and why do we want to write the equation in this form? Because the Hirota derivative simplify exponential function in a remarkably simple manner. Okay, I take, let's say, constant small a small b as a scalar number. The Hirota derivative to the m power of exponential ax exponential bx is just a minus b raised to the m, and the two exponents multiplied together. Again, to prove this particular formula is relatively straightforward. You just substitute into this particular equation and carry out the differentiation. So again, there's no fancy mathematics involved other than differentiation. So if you know simple calculus of differentiation, then you know how to do Hirota operator. Okay, so so let me continue. So what is remarkable is that this particular mechanism allows you to calculate higher order solution. So again, recall that if u is equal to 2 times log f, 2x derivative, f equal to 1 plus exponential alpha x minus alpha squared t will give you 1 soliton. Now, suppose you put in a similar expression in exponential, but with a different parameter, exponential beta x minus this beta squared d close bracket. Then you find that from the interaction term, you go through a kind of a perturbation type calculation. Then you'll find that an exponential alpha plus beta x, but then the perturbation series terminate there. Okay, and then you will have this particular expression for f, 1 plus exponential alpha x, exponential beta x, exponential alpha plus beta x. Then if you plot it out, again, in the days of the 1970s, where you do not have mathematical software, it takes you some time, but today with all this Mathematica, MATLAB, Maple, you can easily plot that. So this is a typical example of a 2-soliton solution. So the vertical axis is the displacement, the 2 horizontal axes are the space and time. So you can see a taller wave kind of catch up with a shorter wave, interact, and they separate. A more illuminating perspective is a top view. Okay, so again, the vertical axis is the displacement, the 2 horizontal axes are the space, space x and time t. So you can see the taller wave kind of catch up with the shorter wave, they interact, and then the taller wave kind of get pushed a little bit forward. The shorter wave got pushed a little bit backward, but after interaction, they remain, or they kind of retain the same identity. So that's why they are called solitons. So, and the beauty of such equation is that you can include a third term. Okay, I have an alpha x exponential beta x. If you include an exponential gamma x, the expression for f become longer, but then it will represent a free soliton solution. And in principle, you can extend it to n soliton, where all the coefficients can be calculated explicitly. Okay, so some of these may be well known to some of you. So now let's try to get to the more complicated, more interesting thing. So the Hirota method is applicable to many integrable evolution equations. Okay, so again, this become a whole subject, a whole industry by itself. In the past 50 or 60 years, it's not possible for me to get into all the application for Hirota method for nonlinear dynamics, but I will just focus on one particular aspect, which is called sometimes called a long wave limit. So for the time being, let's say it's a mathematical technicality, and say that there's an arbitrary phase factor which can be included in each of the exponential factor. So let me see if I can move this out. Cannot. Oh, okay. So recall that the one soliton solution can be written as 1 plus exponential, either you call it alpha or ax minus a cubed t. Now, if you go through the Hirota calculation again, you will find that you can add a constant in the phase. You can add a constant, let's say you call it phi subscript 0 in the phase, and the whole calculation can still go through. Okay, so you can add a constant or arbitrary phase factor in each exponential factor. 1 plus this ax, you can add a phase factor exponential bx and so on. Okay, so let me let me look at the screen. So let me see if there are any questions. So no, everything seems to be going fine. You seem to be able to understand what I'm saying. Okay. Okay. Now you would say add a phase factor. What's the
Professor, there is a question from the audience. You want to answer now or you want to answer later?
Oh, well, let me answer now. What's the question?
Professor Malmer, you can unmute your, Professor, please unmute.
Oh, Professor Malmer, of course, you need to unmute the microphone.
Sorry. Sorry, I forgot. Can you show the previous formula with the phase?
Okay.
Exponential. Yes, this one. Is parameter A real or imaginary?
For the time being real, but eventually when we go to briefer, then there is a complex conjugate wave number. I'll go to that part when we go to briefer.
Yeah, but, well, the simple question is usually when people talk about the phase, in this expression, they write I in front of AX and in front of T also. Why don't you have I here?
Or A eventually can be complex, but for the KdV case, A is real. Because if you put IA for the KdV case, then you get a singular solution.
Okay, thank you.
Okay, yeah. Okay, so physically, what does this arbitrary phase factor mean? This arbitrary phase factor physically corresponds to the initial position of the soliton, because the soliton can start at any position. The nature will not change. It's still a soliton. So this phase factor actually corresponds to the initial position of the soliton, which is kind of Galilean invariant. So this phase factor, physically, when you put it there, corresponds to the initial position of the soliton. But once you do it there, the mathematician kind of look at it in a different manner. Okay, so now you can put an arbitrary constant there. Can I make this arbitrary constant complex too by analytic continuation? Because I can put in a constant there. It does not affect the bilinear calculation, and therefore it in principle can be any number, not just a real number. It can be a complex number, and therefore we can eventually allow that to be complex too by analytic continuation. And again, we'll come back to this point when we derive the rogue wave solution for evolution equation. Okay. So you ask, are you doing something meaningful? Are you just playing games mathematically? So first of all, I would answer very much so. It's very meaningful. And again, historically, again, we are not doing this for the first time. two very sorry, I have a typing Satsuma, not Satsumi. Sorry, again I do it in a hurry. Excuse me for this. So two very senior scientists in the field of nonlinear wave. One is Mark Eplowitz from the USA, and then Satsuma from Japan. They actually utilize this feature of long wave solution, a long wave limit, to derive exact rational solution in two papers, highly cited paper in Journal of Mathematical Physics in the 1970s. And again, I will not go into all the result of that paper, just highlight it. For the case for coordinate Dirichlet equation, unfortunately, you get singular solution. You get solution, but they are not finite. They have singularity for real x and t, so it's not particularly physically meaningful. But for the so-called Kaptov-Chapman-Padriashvili equation, which means the 2 plus 1 dimensional KdV, that means two space dimension x and y and then t, then you get algebraically localized lump solution. Okay, so these are very good results in the 1970s, 1980s, and so on. Okay, so now let's go to the more exciting thing, which is things that is happening in the past 10, 20 years called rogue wave. So the early history is that you have an abnormally large wave from the sea surface. So many sailors kind of report, or not report, or tell horror story of abnormally large waves from the sea surface, and then they attack the ship, causing damage or even the loss of the ship, casualty, and so on. Okay, so this has been known to sailors for over 100 years. And then the first scientific record come in 1995 on New Year's Day, and therefore this wave is also known as a New Year's wave, January 1st, 1995. I hope I pronounce this word correctly. The Drachner wave. The Drachner wave come from an offshore platform in the North Sea in Europe, and then because they have scientific instrument there, they can record this particular wave, and then things took a strange turn in a paper in Nature in 2007. They report similar wave in the optical fiber, and now this study of rogue wave become again an industry in itself under this very broad topic of extreme and rare event in physics. Okay, so perhaps let me say something about rogue a few feature, and then if I can make the video work, I'll show you a YouTube video which I show in my class too. Okay, so let me say something on rogue wave and briefer. So rogue wave typically study under this infinite or semi-infinite domain. So wave come from nowhere and disappear without a trace. And then briefers are pulsating mode under periodic boundary conditions. So depend whether you are talking about infinite or semi-infinite domain or a periodic boundary condition and so on. So now let me see if I can show this particular video. This is actually a YouTube video. So so let me show this. So I hope you can all see this, right? Let me see. If you cannot see this, voice it or say something to me. Otherwise, so the point is the following. The point I want to show this video is following. Now this is a very small boat sailing on the sea. So you can see this is not a stormy condition. It's not a typhoon. It's not a hurricane condition. There's some wind, some waves, but it's not a typhoon condition, not a hurricane condition. So the point is, can you kind of see or predict when a wave will suddenly come out from the ocean and attack this particular ship? Okay, so I'll quickly show you something like less than 2 minutes. So see if you can. In the interest of time, I'll go fast forward a little. So I thought that this was a rogue wave, but it's not actually. See, this suddenly you have a wave coming out from nowhere. So actually, I have many other videos like of this nature, but again, in the interest of time, I'll just go quickly first. So you have rogue wave, kind of unexpectedly large, surprisingly large displacement from an otherwise tranquil background and attack shifts, or in the case of optical fiber, an unexpectedly large signal. Okay, so for a periodic boundary condition, we have something called breathers. And now going back to what I say 10 minutes ago, Hirota method can be used to find multi-soliton solution. So concerning the question raised by Professor Mello minutes ago, for KDV equation, you usually set the parameter real, but for the so-called nonlinear Schrodinger equation, we set the parameter, or we allow the parameter to be complex. And in particular, for a two-soliton solution, in general, if you choose a pair of complex conjugate wave number, then you can derive a pulsating mode, which are known as breathers. Okay. So what is our contribution? So again, I'll just explain it in simple terms without going through a lot of calculation. Our contribution is to kind of use all these ideas together. So we use a complex conjugate wave number. We allow a complex phase factor, and we allow long wave limit too. We combine all these ingredients together, and then we can derive a rogue wave solution. And this paper was published in the Journal of Physical Society of Japan in 2013. So we apply this to a case of so-called long wave short wave resonance. And long wave short wave resonance arises when we have a system with many wave modes, some long, some short. And whenever the phase velocity of the long wave matches the group velocity of the short wave, then you will have some kind of, this is the idea of calculus, but let me show you the paper first, okay? So, let me show some. Okay, sorry, let me change the magnification a bit. Again, do not be scared or discouraged by this, especially the young researcher in the audience. Just go over the qualitative scheme of things. So we have two dependent variables here. Mathematically, we have a complex variable S and then a real variable L. Physically, what we have is that we have a short wave envelope denoted by capital S, and then a long wave component, which kind of related to a mean flow in fluid mechanics, which is in resonance with the short wave. And then their evolution is dictated by this dynamic. So the evolution S subscript T time derivative is related to the dispersion 2x derivative, is driven by the long wave L on the right-hand side is some kind of forcing term. And then the evolution of L itself, L time derivative, is driven by the so-called radiation stress, the SS star term with X derivative. So they are coupled together. And then you can use the Hirota method first using this auxiliary variable transformation S equal to small t divided by F. Small t is complex, small f is real. And then again, this familiar pattern 2 log f, 2x derivative. And then you can obtain this particular bilinear form. And then you can also write down a two-soliton type solution. But this time, let me show the again, I won't go into all the technical details. Then you start with a 2-soliton type solution. But this time we use some kind of complex conjugate wave number. So you can see I put an exponential IPX and an exponential minus IPX. And then I try to do a long wave limit expansion. So again, I just show the main point of the calculation here. Okay? So this is the main point of the calculation. So again, the main ingredient are complex conjugate wave number to get some kind of briefer type mode. And then we take a long wave limit, and then that means the wave number P going to 0. But then if you just do that alone, you still cannot cancel out the leading order term. You need the complex, the phase factor to produce a -1. So if you just look at the first line of the equation, you have 1 plus exponential, exponential, and then exponential P plus P star. If you don't do anything to the complex conjugate factor and you do a long wave limit, and all of the factor will just give you 1. Exponential 0 is 1. But somehow, if we allow this complex phase factor to be -1, then I have 1 minus exponential px minus exponential p star x, and then exponential p by p star. I also expand it, and from elementary calculus, e to the px is 1 plus px, p squared x squared over 2, and then you do the same thing for p star. And then for the constant term, you can write it as some kind of m0 pp star. And the miraculous development, if I can say that, is that the leading order term, the 1, cancel out. The linear term p and p star cancel out. And then you just have the pp star, the quadratic term, which is left behind. And then you have something like roughly x squared, which is always positive, plus another constant, which is always positive, and therefore you have a non-singular solution. And then you have pp star, and you ask, okay, what happened to the pp star? Does it make the expression 0? The answer is no. The magic formula is that the let me go back to the the magic formula for this type of calculation is that the long wave is given by 2 times log f. So even though there's a pp star, you take the log of that, is log of pp star is a constant. When you do 2x derivative, that part is gone. And then eventually what you will be having is just this m0 plus x squared, and this non-singular algebraic expression will give you a log wave. Okay. Okay, so let me see how am I doing in terms of time. I'm almost running out of time. Okay, so the kind of almost to the last part of the talk will involve even more calculation, but I'll try to be qualitative and just introduce again the idea to the beginning researcher and to the established researcher. I just explain in a qualitative term what we are doing. So what we are trying to do is to show how some of these exact solution or exact formulation of nonlinear evolution equation can provide illuminating insight for this classical problem of Fermi-Pasta-Ulam-Tsingou recurrence, or I'll just call it FPUT. So what is FPUT? In very qualitative manner, FPUT is a tendency or property of a multimode system to return to the initial state after complex stages of nonlinear evolution. So you have, let's say, one or many partial differential equations which are infinite dimensional Hamiltonian system. So they can allow many modes. And if you start with an arbitrary initial condition, in general, you have a very complicated dynamical picture. But for very special situation, this multimode system might kind of go back to the initial state after complex stages. Okay, so periodic boundary condition in the so-called transverse variable, and then what we are going to say is that we can derive a doubly periodic solution, and this doubly periodic solution will be a manifestation of this FPUT phenomenon. And if you think this is purely theoretical, it's not quite so. This has been under experimental investigation for many years, starting with experiment in water waves in the 1970s and in the optics in the past 20 years. And since we have some very established researchers like Professor Mellomet here, but nevertheless permit me to quote one recent paper. This paper come out in the journal Optics Express in 2020, in which people demonstrate FPUT, this recurrence in the optical setting. Let me show the diagram. Again, I'm not a person who do experiment, so I can only show this particular paper in optical experiment to try to convince you that there are people who do very elaborate experiment to demonstrate this FPUT recurrence. And again, I will just show the main kind of result. So again, we have first harmonic, what we call this triangular spectrum. Again, I omit all this detail. I just ask you to look at this particular diagram on the lower left-hand corner, in which you have the amplitude or the intensity of the light pulses in both the propagation and the transverse variable. So obviously, the red color represent the places or the time with high amplitude, so you can see a doubly periodic pattern. So we will try to now say more about this doubly periodic pattern, again qualitatively, because we just have something like 15 minutes left or so. So again, in very qualitative term, I want to say something about elliptic and theta function. Okay. So what are elliptic function? Okay, so again, in very qualitative sense, they are generalization of the trigonometric function. So elliptic function have a modulus, and when that modulus go to 0, you go back to the trigonometric function. When that modulus go to 1, you have a hyperbolic function. And if that modulus between 0 to 1, then you have a genuine elliptic function. Now, again, I just say in a very few words, very qualitative manner. So if you like mathematics in the form of geometry, if you calculate the arc length of an ellipse, then you get an elliptic integral, which is an inverse of an elliptic function. So geometrically, elliptic function arises from the arc length of an ellipse. But if you are a very analytic person, you like mathematical analysis, elliptic function are what we call doubly periodic meromorphic function. So if you look at the complex plane, and if you insist that all the singularities are posed, okay? If you insist that all the singularities are posed, no branch point, no essential singularity. Again, no branch point, no essential singularity, plus the fact that that function has to be doubly periodic, periodic in the real variable, periodic in the imaginary variable. Those kind of functions, doubly periodic meromorphic function, are elliptic function. Okay, so what are theta functions? So theta functions are represented by Fourier series of exponential decaying coefficient. Okay, so your first reaction is big deal. What is this term about? So let me again go back to very elementary thing. Suppose we go back to an undergraduate class where we teach or at least this is the way I teach. We teach engineering mathematics to engineering undergraduate students. So an important topic is Fourier series. Okay, so we tell the undergraduate that if a function has continuous first derivative, continuous second derivative, but discontinuous derivative of order p, then the Fourier coefficient will decay like order 1 over n to the p. Okay, now to illustrate things, again, I use very elementary example to not to scare you all or something. So suppose I have a step function, so which is, let's say, k from 0 to pi minus k from pi to 2 pi and so on. And you try to calculate the Fourier series, then it will be sine x, sine 3x over 3, sine 5x over 5. And you can see indeed the Fourier coefficient decay like order 1 over n, okay, because the function is not continuous. Now, if you look at x squared, X squared, if you plot it, it will be a parabola from -1 to 1, but Fourier series is a periodic function, so it will be part of a parabola from -1 to 1, 1 to 3, 3 to 5, 5 to 7, and so on. So the function will have a discontinuous derivative at the two ends, and if you calculate the Fourier series, indeed, the Fourier coefficient decay like n squared. So these are standard results, but then the insight we ask you to gain is that function discontinuous derivative Fourier coefficient decay like 1 over n squared. And so let me show you what a real theta function will look like. These are the theta function that you will find in any standard handbook. So again, there's a small parameter q, small q between 0 and 1. And if you raise it to q to the n square, q to the n plus 1/2 square, and so on. And again, I'm not bothering you with all this precise formulation, but these are the so-called theta function, Fourier coefficient with exponential decaying coefficient. And then it turns out that elliptic function can be expressed as a ratio of theta function. All these the so-called Jacobi elliptic function SNCN can be expressed in this form. So again, these are very elaborate mathematical functions, but just we express it in terms of ratio of Fourier series. Okay. Okay, so now I only have 10 or 5 minutes to introduce a very important canonical equation known as the nonlinear Schrodinger equation. So physically, it's the evolution of a slowly varying packet under quadratic dispersion and cubic nonlinearity. Okay, so a complex envelope A, you have IAT, slow time, and AXX, the second order dispersion, cubic nonlinearity. Then the properties of the solution depend in a critical manner on the relative sign of the dispersion and cubic nonlinearity. The top one is called the focusing regime. The bottom one is called the focusing regime. Okay, so again, this is a huge topic. Let me go back to here. Doesn't work. Okay, so. And I just Google search it. If you look for nonlinear Schrodinger equation, there are actually 29,000 papers. So I hope you can convince this indeed a very important subject. And the meaning of T and X are different depending on application in fluid mechanics. T is slow time, X is group velocity coordinate in optics. T is actually propagation in space, and X is retarded time. So again, sometimes I am more using the word time and space because they mean different things according to fluid mechanics, according whether you're in fluid mechanics or optics. Okay, so now let's go to the final topic. Is more elaborate, more intriguing. So I'll just outline in a few slides. It's actually an active area of research. So I hope I can convince some beginning researchers there's something interesting going on in this area. So first, I quote a few doubly periodic solutions of the focusing nonlinear Schrodinger equation. So some of the paper I find in the well-established literature by Emilia Mihalacci and in Physical Review A 1993, and myself, we published a paper in Wave Motion in 2002. Okay, so this thing doesn't work well. So let me show you the solution first, okay? So in the late 1990s, I was reading the literature, and I read those two papers in the Physical Review A, and I come across this particular solution. So my first reaction is, how can anyone deduce a solution like this for the nonlinear Schrodinger equation? I don't think I can do it without any help. So at that time, I was reading elliptic and theta function. So my reaction is, if I express it in terms of theta function, will it help? I mean, to interpret this solution. So indeed it does, and the theta function solution look like this. To you, may be worse because there are so many simple floating around, but somehow I kind of see some kind of pattern in the theta function solution, and I can extend this particular pattern to other evolution equation, not just a nonlinear Schrodinger equation. We can do it the so-called Davis-Silverson sine Gordon. We can do it once you see that pattern in theta function. So again, I will not go into all the details here. So I'll just tell you the rough idea of what we are doing. So this particular solution, you have 4 parameters and 2 constraints relating this 4 parameters. The 4 parameters are the k and k1, which are the distinct moduli of the Jacobi elliptic function. And then you have the wave number in the transverse and propagation variable. And then 2 constraints relating these 4, and therefore you have 2 degrees of freedom. So again, the main point is you have doubly periodic solution for many evolution equations. The nonlinear Schrodinger equation being an important canonical example, but you have many others too, like Davis-Silverson, sine Gordon. These are the things that we are actively pursuing. Okay, so we have doubly periodic solution. K1 are the distinct parameter. Okay, so I already gone through this. Okay, so now again, I just summarize a very simplified version of a very complex nonlinear dynamics system. So let's say you want to study a complicated system, let's say nonlinear Schrodinger, Davis-Silverson, or whatever equation you can name it, under periodic boundary condition. Then the physical picture we are proposing is that we have linear disturbance which grow as a result of something called modulation instability. And as this grows, it excites the higher harmonic, and then you have a so-called triangular spectrum. And eventually almost have or attain more or less the same magnitude at one instant in space or time. Then you have breathers. And once these breathers are formed, they do not kind of maintain a steady state. They will decay. And these are pulsating mode, they will decay. And when it decays to a very small amplitude, modulation instability resume. And then you will have growth again, and then you will form the breather again. And then eventually this phenomenon recur, and then you have this recurrence which come out, which can be observed in the optical pattern I showed minutes ago. Okay, and what we propose is that these kind of recurrence can be described by the doubly periodic solution we just outlined. Okay, so again, I kind of run out of time here. I only have something like 5 minutes left, so I'll use the last 2 or 3 minutes to kind of highlight the main point that we have discussed. So starting from the very elementary aspect, solitons are propagating mode arising from a balance of dispersion and nonlinearity. There are many ingenious methods like the inverse scattering method, background transformation method, Darboux transformation method. But in this particular talk, we just highlight the Hirota Bilinear method, which is a conceptually simple method scheme or method to establish exact solution. And we can use long-wave limit to yield rational solutions. So these are well-established literature in the 1960s, 70s, and 80s. So fast forward in time, we go to the 1990s, year 2007, then we study rogue wave as unexpectedly large displacement from a tranquil background. And then we have the briefer things too. And then now finally fast forward to things happening in the past few years, or past 8 or 9 years. Briefers may recur periodically as a manifestation of this FPUT phenomenon. So with that, perhaps I will stop here. And then again, I have to thank the organizer for organizing this talk. And thank you to all of you for showing up at this particular seminar. So let me stop share at this point and hope to go back to the background. Okay.
Thank you, Professor. Thank you.
Okay.
So now the forum is open for questions, clarifications, doubts. Yes, Professor Malman, go ahead.
Yeah, okay. Thank you, Kwok, for the very interesting talk. And the question, if you have a rogue wave solution produced by the integrable equation, and then you add some additional term which breaks the integrability, what will happen to the rogue wave?
I can only say this is an active field of research. What our group is doing, we study a so-called structural robustness. That means you have an exact rogue wave solution. We put in some random noise and see whether the rogue wave can still come out. And of course, the answer is that some can still maintain and come out as a rogue wave. Some are kind of destroyed or kind of contaminated by the background modulation instability. So it perhaps permit me to give this answer. It depends very much on which equation you are studying. But let's say for the rest of the audience, a very current area of study in the past, especially the past 2 or 3 years, is to study rogue wave on a periodic background. So in the past 10 years, people focus on rogue wave on a plane wave background. But in the past 2 or 3 years, people study rogue wave on a periodic background, where the background itself is some kind of periodic wave and not a plane wave. And some of the mathematics involved are really difficult. And again, we have interesting numerical simulation. And if any of you are interested, and I have collected some kind of literature, and I can send you those papers for you to kind of look into these particular topics.
Okay, thank you.
Yeah, thank you, Professor Mello.
Yeah, Prasad, you can raise your question now.
Yes,
Yes, Prasad, go ahead.
The initial transformation, like for in this case, the so is it clear?
No, your voice is not clear. Can you write it in chat box?
Yeah, but you can write it in the chat box because
Yeah.
the transmission of the voice is problematic in the microphone.
In the meantime,
So is it
other
audible?
questions? Yes.
Hello.
Yes. Prashant, better you put it in the chat box. Yeah.
Oh, okay, so if there are other members of the audience who have,
others,
yeah.
Are there any? Murugesh, do you have some doubts?
So again, let's say, especially for the younger audience, please do not feel shy. Just
Ramakrishnan. Yeah, he put it in the chat box.
particular how we define the log volume. So
Professor, are you able to read your chat box? You already put the question in the chat box.
So, but then I think I need to share screen again. Because, so let me. I guess you mean this particular question, this particular page, right? Okay, so if you ask how does Hirota come up with this ingenious transformation U equal to 2 log f xx and so on, I can only say that it's pure ingenuity, and actually there's a large element of trial and error and perhaps luck in that particular aspect. Okay? So permit me to be a little bit informal here. So a joke in the nonlinear wave community is that, so what is the Hirota method? The Hirota method is that you write down a nonlinear evolution equation and then you send it to Hirota. He will send you back the solution. So that would be called the Hirota method. But of course, the actual process in arriving at the correct transformation require a lot of intermediate work. And right now we have all this software, mathematical MATLAB that make the calculation easier. But back in the 70s and 80s, we don't have all this software. Okay, so yeah. But the constraint of the Hirota method is that it can be used for multi-soliton only. It cannot solve for the initial value problem. Inverse scattering transform can, in principle, handle an initial value problem. But of course, eventually the calculation of inverse scattering transform is very involved too and might involve some numerical work, which might, for the KDV case, you might start to do it numerically from the start. Okay, so so the choice of a method depend on experience, depend on a certain extent luck too. Yeah.
Prashant, is that clear?
And so what kind of perturbation we are going to use? Okay, so typically we only use exponential function for localized solution. For soliton type, briefer type solution, we use exponential function. But for doubly periodic type solution, you need more fancy thing like elliptic and theta function. Okay? So this is a general answer. Yeah. Again, to younger members of the audience, we again encourage you to speak out. Okay.
So, are there any other questions from the audience?
Again, the whole field of the things that I mentioned actually involve a lot of literature, but I just simplify things, hopefully to a level where beginning graduate students and people not involved in solitons can kind of see what is going on. But I hope some of you will find some aspect of what I have talked about to be relevant to your work, and then you can write an email to me. I can send you the relevant paper to see if this very interesting, this very dynamic field can provide additional insight for your own research work. Or dissipative system in general cannot. Dissipative system in general are not conservative. Hirota method will have difficult usually to treat dissipative system. there are one or two exceptions. There's something called Becky and Nosaki modification of the Hirota method. Again, I can send you the paper rather than writing things on the screen. But one or two exceptions called Becky and Nosaki where you can do or can handle cases of the complex Ginsburg-Van Daan equation, which is a dissipative system. Okay, but in general, the calculation there are very involved too. So unless you really are looking for special exact solution, you might as well do it numerically from the start. Yeah.
Prasad, okay. Do you have any more questions, Prasad? Okay. So, is there any other question from the participants or students? You need some clarifications. Okay, Professor, we are not receiving more questions.
Oh, fine. They are too shy. Yeah.
Maybe they will write to you.
Yeah.
Okay. So, since there are no more questions, I would like to conclude the session by thanking Professor Chow for accepting our invitation and giving a very elementary talk to us. Thank you very much, Professor. Thank you.
Thank you. Thanks to the organizer. Thanks to all of you for attending this talk. I hope we can continue to have some kind of cultural exchange in the future. Yeah. Thank you.
Yes.
Okay.
Thank you.
Okay. Bye-bye.
Bye.
Bye-bye.